Yes, welcome to this video. So in this video, we'll discuss unit number 2 of the chapter, the course partial differential equation vector calculus. In unit number 2, generally there are 3 different parts. The first one is solving a higher order partial differential equation with constant coefficients, which is homogeneous. And the second part, solving a higher order partial differential equation with constant coefficients, which is non-homogeneous. So in this video, we will restrict ourselves to only homogeneous linear DE. First, let us know what is the difference between homogeneous and non-homogeneous. So I'll explain on the board. Yes. So the title of our video is partial differential equation of higher order. Generally, we'll write for nth order with constant coefficients. Partial differential equation of higher order with constant coefficients. Okay. So in this chapter, we'll consider the following notation. So let Z be a function of two variables, x and y. X and y are independent variables, and Z is depending on both x and y. So we use the following notation. Dou by dou with respect to x, dou by dou x will be denoted with capital D, and dou by dou y will be denoted with capital D dash. And any other derivative of any other order derivative with respect to x. For example, nth derivative with respect to x will be denoted by d power n, and nth derivative with respect to y will be denoted with d dash power n for all n from 2, 3, 4, and so on. Okay, we'll follow this notation throughout this particular unit number 2 of partial differential equation vector calculus. Okay, so with this notation, so let us consider this. So a PDE of the form nth derivative of z with respect to x plus some constant k1 into nth derivative of z n minus 1 times with respect to x and 1 time with respect to y plus another constant k2 into nth derivative of z n minus 2 times with respect to x and 2 times with respect to y, and so on. If you go on like this, then k n minus 1 into nth derivative of z 1 time with respect to x and n minus 1 time with respect to y plus kn into nth derivative of z 1 no time with respect to x and all the n times with respect to y equal to 0, where all these ki's, k1, k2, and so on, etc., all these k's are constants. So consider this equation. So let us name this as some equation number 1. Okay. Then this equation, so this is called a homogeneous linear PDE with constant coefficients. Homogeneous linear partial differential equation, simply PDE with constant coefficients. Here every word has a separate meaning. So why it is called homogeneous? Because the right hand side function is 0. Why it is called linear? Because the power of every derivative, every term contains derivative of first degree only. Okay. Next, why it is called PD with constant coefficients? All the constants k1, k2, and so on up to kn, they are all constants. Okay. Now, to solve this equation, there are only 2 steps. The first step is finding the complementary function, and second step is writing the complete solution. So method of solving contains only 2 steps. So method, in step 1, we'll find the complementary function, simply CF. We'll call this as complementary function. Okay, complementary function, also known as CF simply. And in step number 2, directly we will write the complete solution. The complete solution, that is also denoted by CS. So better to write the complete word. The complete solution is simply the dependent variable z equal to CF. That's it. Only 2 steps. So once the first step is completed, once we find the CF complementary function step number 1, then we can declare the general solution as z equal to CF, where z is the dependent variable. Okay. Now, so the entire process depends on step 1 mainly. So to explain step 1, generally we'll consider n equal to 3, because in the examination we'll get maximum up to 3rd order. So let us not confuse ourselves by considering 4th, 5th, and 6th degree equations. We'll consider only up to 3rd degree. Okay. Yes. So let us consider. So let us consider a 3rd degree equation only. So dou cube z by dou x cube plus some constant k1 into dou cube z by dou x square dou y plus a constant k2 into dou cube z by dou x dou y square plus another constant k3 into dou cube z by dou y cube equal to 0. This is general 3rd order linear PDE with constant coefficients. So in our standard notation, this can be written as dou by dou x is capital D. So dou cube by dou x cube means capital D cube operating on z plus k1 into 2 derivatives with respect to x and 1 derivative with respect to partially. So d 2 times and d dash 1 time operating on z plus k2 into, out of the 3 partial derivatives, 1 derivative with respect to x and 2 derivatives with respect to y. So d dash square operating on z plus k3. Here all the 3 partial derivatives are with respect to y only. So d dash 2. So all these are operating on z in each term, giving us 0. This is the simplified form of this partial differential equation. Then step 1, complementary function. So the process is, first we'll write the auxiliary equation. Auxiliary equation. The auxiliary equation is given by, simply put d equal to 1 and d equal to m and d dash equal to 1. So m cube plus k1 into m square into 1 plus k2 into m into 1 square plus k3 into 1 cube equal to 0. So in this operator, simply replace d with m and d dash with 1. Then we will get a cubic equation. So solve this and find the 3 values. Solve this and find the 3 values of m. Since this is the cubic equation, we will get 3 values. So let us name them as m1, m2 and m3. We will get 3 values. Let us name them as m1, m2, m3. Then the complementary function will be given like this. So nature of roots. These m1, m2, m3, they may be equal, they may be different, or 2 may be equal, third one may be different. So based on the values of this m1, m2, m3 only, we can write the complementary function. First, if m1, m2, m3, if all the 3 are distinct, means no 2 are equal, then the complementary function will be written as some function of y plus m1x plus another function f2 of y plus m2x for the second root m2 and another function f3 of y plus m3x. So here f1, f2, f3 are 3 arbitrary functions. This is the complementary function. If m1 and m2 are equal, but the third one is different. Out of the 3 roots, first 2 are equal. Take m2 equal to m1. In that case, what we'll do is, in the same complementary function, in place of m2, we'll write m1, but outside we'll put m1x. So f1 of y plus m1x plus x into f2 of again y plus m1x plus third one same f3 of y plus m3x. Okay. Now, if all the three m1, m2, m3 are equal, m1, m2, m3, if all the three are equal, then here in place of m3 also write m1 and multiply with x square. So f1 of y plus m1x plus x into f2 of y plus m1x plus x square into f3 of y plus m1x. So this is the procedure of finding complementary function. This is our step number 1 in solving linear partial differential equation which is homogeneous. When the right side is 0. Okay. And second step. The second step as per the procedure is writing the complete solution. So the complete solution, we'll write simply CS. The complete solution of the given partial differential equation is the dependent variable z equal to CF. That means z equal to case 1, case 2 or case 3. The function derived in step number 1. So this is the process. So very simple. So the only thing we have to do is we have to solve the auxiliary equation. If it is a second order equation, we will get only 2 roots, m1 and m2. If it is a third order equation, we will get 3 roots, m1, m2, m3. So in the examination, we will get up to maximum 3. So we need not go for 4th, 5th and 6th orders. We need not confuse ourselves. Okay. So to understand this procedure, we will do 2 problems. Okay. So problem number 1. Solve the differential equation 2 into dou square z by dou x square 2 into dou square z by dou x square plus 5 into dou square z by dou x dou y plus 2 times dou square z by dou y square equal to 0. So consider this differential equation. 2 into dou square by dou x square plus 5 times dou square z by dou x dou y plus 2 times dou square z by dou y square. This is the differential equation. First of all, identify the name of this equation. First of all, is it homogeneous? Yes. Right hand side is 0, so it is homogeneous. Then next, the coefficients are 2, 5, 2. All are constants. Next, every term contains partial derivatives, that too with power 1 only. Second order, first degree. So the degree of each and every term is 1. So this is a linear partial differential equation with constant coefficients and order is 2. Okay. So in the notation form, so to solve this, first express this equation in the notation form. So in the standard notation, the given differential equation is 2 into second derivative with respect to x of z plus 5 into, out of the 2 derivatives, 1 derivative is with respect to x and 1 derivative is with respect to y. So we'll get d dash of z, and third one, 2 times, both the derivatives are with respect to y. So d dash square of z equal to 0. That means 2d square in the first term, 5d dash in the second term, and 2d dash square in the third term are operating on z yielding 0. So this is the given differential equation in the simplified form. Now coming to step number 1. So as per the procedure, in this operator, by replacing d with m and d dash with 1, we have to write the auxiliary equation. So the auxiliary equation is given by replace d with m. So first term will become 2m square. Second term will become 5 into m into 1. Third term become 2 into 1 square equal to 0. So consider only the operator in terms of d. So it is of the form f of d dash. So in place of d put m, in place of d dash put 1. No, this is a second order equation. So can you solve this? Yes. 2 2's 4 and 4 into 1 is 4, 4 plus 1 5. So we can write this as 2m square plus 4m plus m plus 2 equal to 0. From the first two, we can take out 2m as common. So 2m into m plus 2. From the last two, we can take 1 as common. So we'll get m plus 2. Now again from these two, after taking out m plus 2 as common, we will get m plus 2 into 2m plus 1 equal to 0. So m plus 2 equal to 0 means m equal to minus 2. And 2m plus 1 equal to 0 means m equal to minus half. So we got two roots. Both are real and distinct. Okay. So let us name the first one as m1. So let m1 equal to minus 2. And let us take the second one as m2. m2 equal to minus 2. So clearly m1 and m2 are not equal. So this comes under case 1. Already we discussed the procedure. When the roots are distinct, how to write the complementary function. When the roots are equal, how to write the complementary function, and so on. Therefore, complementary function as per the procedure is correspond to the first root, some function f1 of y plus m1x, and correspond to the second root m2, some function of y plus m2x. Okay. So in this problem, what is m1 minus 2? So some function of y minus 2x plus another function of y minus half x. So y minus x by 2. So this is complement. This is step number 1. And step number 2 is we have to write the complete solution, the CS. So the complete solution is given by the complete solution is the dependent variable z equal to CF. So z equal to CF means this f1 of y minus 2x plus f2 of y minus x by 2, where f1 and f2 are arbitrary functions. We have to mention clearly what is f1, what is f2. f1, f2 are two arbitrary functions. They can be any functions. So they are called arbitrary functions. Okay. So this is the method of solving an equation. So here the two roots are different. If the two roots are equal, if m1 and m2 are same, then before f2 will get 1x. So this is example number 1. Now example number 2. Now let us take an equation. We'll consider third order equation. Okay. In which out of the three roots, two are equal and the third one different. We can take such example also. Okay. So let us take one example where the out of the three roots, two roots are equal and third one is different. Okay. Solve dou cube z by dou x cube, dou cube z by dou x cube minus 3 times dou cube z by dou x square dou y plus 4 times dou cube z by dou y cube equal to 0. So consider this equation. Okay. So as per our standard notation, this equation can be written as, so this PDE can be expressed as in the standard notation, that is dou by dou x with d and dou by dou y with d dash. If we denote that, then the PDE can be expressed as, in the first term we will get d cube z, in the second term we will get minus 3 into d square d dash of z, in the third term we will get 4 into d dash cube of z equal to 0. Okay. So step 1. In step 1, we have to write the auxiliary equation. So the auxiliary equation, simply I will write EAE. The auxiliary equation is replace d with m and d dash with 1. So first term becomes m cube, second term becomes minus 3 into m square into 1 plus fourth one becomes 4 into 1 cube equal to 0. So m cube minus 3m square plus 1 equal to 0. It is a cubic equation. And we know that for a cubic equation, there will be three roots. And we have to find the first root by trial and error method. You know what is trial and error method? We'll substitute m equal 1. if m equal 1 satisfies this equation, then m minus 1 will be one of the factors of this polynomial on the left hand side. Similarly, if m equal minus 1 satisfies this equation, then we'll take m minus of minus m plus 1 as one of the polynomial. So clearly, for m equal to 1, we will get 1 minus 3 plus 4, not equal to 0. For m equal to minus 1, our LHS becomes minus 1 whole cube minus 3 into minus 1 whole square plus 4. So what we'll get? Minus 1 minus 3 minus 4 plus 4 equal to 0, equal to RHS. That means clearly m equal minus 1 is the root of this equation and m plus 1 is a factor of the polynomial. So if you name this equation as 1, then this implies, our equation 1 can be expressed as m plus 1 into some polynomial, some quadratic polynomial. That cubic polynomial can be expressed as m plus 1 into some quadratic polynomial equal to 0. So now we have to identify what is that quadratic polynomial. So to get that quadratic polynomial, what we have to do is we have to divide the cubic polynomial m cube minus 3m square plus 4, which we have obtained in the last page. See, we have to divide this m cube minus 3m square plus 4 with this m plus 1 to get the quadratic polynomial. Means simply we have to go for division. So if we divide m cube minus 3m square plus 4, if we divide that with m plus 1, what we will get? To get m cube, we have to multiply m with m square. Now m plus 1 into m square becomes m cube plus m square. So minus minus, these two will be cancelled. So minus 3m square minus m square minus 4m square plus 4. Now to get minus 4m square, we have to multiply m with minus 4m. So m plus 1 into minus 4m. So minus 4m square, 1 into minus 4m minus 4m. So if we subtract, this will become plus, this will become plus, this will be cancelled. 4m plus 4 will be there. Now to get 4m, we have to multiply m with 4. So we will get m plus 1 into 4, 4m plus 4. If we subtract, we will get 0. So this is the other quadratic polynomial. Okay. Therefore, our equation 1 is now expressed as m plus 1 into this quadratic polynomial m square minus 4m plus 4 equal to 0. Now clearly we know that m square minus 4m plus 4 is nothing but m minus 2 whole square. So this is nothing but m plus 1 into m minus 2 whole square equal to 0. So clearly minus 1 is one root and 2 is a repeated root. So let us start take with 2. So 2 minus 1, they are the roots. So we'll take m1, m2 as 2 and m3 as 3. So let us take m1 equal to m2 equal to 2 and m3 equal to minus 1. So m1 equal to m2 and that is different from m3. Out of the 3 roots, 2 roots are equal and third root is different. So as per the procedure, how to write the complementary function? So the complementary function as per the process, this is nothing but corresponding to the repeated roots m1, m2. We will get some function of y plus m1x plus x into another function of again y plus m1x. In place of m2, we'll write m1 plus correspond to third one, f3 of y plus m3x. This is the formula as per the procedure. So f1 of y plus what is m1? 2. m2 is also 2. So x into f2 of y plus 2x. And what is m3? Minus 1. So y minus x. So this is the complementary function. This is step number 1. Okay. In place of m2, we will write m1 and put x outside as one of the factors. So the step 2 is, so the complete solution or the general solution is given by z equal to cf. So this implies z equal to this entire thing, f1 of y plus 2x plus x into f2 of y plus 2x plus f3 of y minus 3x, where all these three, f1, f2 and f3 are arbitrary functions. So This is the solution of the given problem. Okay, so just go back to our right from the starting one. We'll discuss. See, so partial differential equation higher order with constant quotient, that is the topic of this video. So if we take x and y as independent variables, and if we use the symbol z for denote the independent variables, then z depends on x and y, means z is a function of x and y. So throughout this unit, we'll use this notation: dou by dou x with d, dou by dou y with d dash, and nth ordered partial derivative with respect to x with d power n, and nth order partial derivative with respect to y with d dash power n, for all n from 2 to infinity. Then any combination of various nth order partial derivatives. First term, all the n partial derivatives with respect to n. Second term, out of the n partial derivatives, n minus 1 with respect to x and only 1 with respect to y. Next term, n minus 2 derivatives with respect to x, 2 times with y, and so on. The last one, all the n partial derivatives with respect to y. That means as you move from left to right, the number of derivatives with respect to x are decreasing, n minus 1, n minus 2, and the number of partial derivatives with respect to y are increasing, y square, and so on. When the right hand side is 0, it is said to be homogeneous PDE. If all these k1, k2, and so on up to kn are constant, then this is said to be homogeneous linear PDE with constant coefficients. Okay. Now, in our syllabus, we will restrict ourselves to only second and third order. So, by taking a second and third order, we'll discuss the procedure. First, the procedure of solving this particular PDE will contain only 2 steps. The first step, finding the complementary function, and second step, writing the complete solution. Okay. Now, so I am writing the procedure for a general third order linear PDE with constant coefficients, which is homogeneous. So generally, this is the general form of a third order linear PDE. So as per the notation introduced in the last page, so the first term will become d cube of z, second term will become k1 into d square d dash of z, third term becomes k2 into d dash square of z, and fourth one k cube into d dash cube of z. Now by replacing d with m and d dash with 1 in this operator on the left hand side, we will get an equation in terms of m. We will name that as auxiliary equation. So in this case, in place of d, if you write k, then first term becomes k cube, second term becomes k1 into m square into 1, so k1 m square. Third term becomes k2 into m into 1 square, k2m. Third term becomes k3 into 1 cube, k3 equals 0. See, this is a cubic equation. By solving this, we will find the 3 values for m. We will name them as m1, m2, m3. m1, m2, m3 may be equal, may be different, or 2 may be equal, third may be different. So we'll consider all the cases. If m1, m2, m3 are all distinct, then we'll write the complement function as some arbitrary function f1 of y plus m1x plus some arbitrary function f2 of y plus m2x plus some arbitrary function f3 of y plus m3x. If the first two units m1, m2 are equal, then in the complement function in place of m2 we'll write m1 and we'll multiply outside with x. What is the purpose of writing into x? Because if we don't write x, then f1 of y plus m1x plus f2 of y plus m3x. Since both are function of y plus m1x, by combining those two, we can write only one function. But we need 3 arbitrary functions in the solution of a third order PDE. That's why, in order not to combine these two, we are multiplying with x outside. That is the reason. And if all the 3 m1, m2, m3 are equal, then in place of m2 write m1, in place of m3 also write m1, multiply second term with x, third term with x square. This is the step number 1. And step number 2, yes, just wait. In step number 2, we'll write the complete general solution, the complete solution as z equal to complementary function. Okay. Now we'll consider 2 examples: one first order equation, one second order PDE, one third order PDE. So this is the second order PDE. The first term contains second order derivative of z with respect to x. This is second order derivative of z, one derivative with respect to x and one derivative with respect to y. This is second order derivative of z with respect to y partially. So as per the notation, this becomes 2d square of z, 5 into d dash of z plus 2 into d dash square of z. Okay. So the auxiliary equation is replace d with m and d dash with 1. So we'll get 2m square plus 5m plus 2 equals 0. By solving this, we'll get m equal minus 2 minus 7. So both are different. M1, M2 both are different. Okay. So we'll take minus 2 as M1 and minus of as M2. So M1 not equal to M2. So as per case 2 of the procedure, CF will be correspond to minus 2. There will be a function of the form, some function of y plus m1 x correspond to the M2, some function of y plus m2x. So in place of M1, write minus 2. In place of M2, write minus 2. So this is the calculated function. And the second step is the complete solution z equal to CF. So z equal to this f1 of y minus m2x plus f2 of y minus half of x. Here f1, f2 are arbitrary. Now take another example. Dou cube z by dou x cube minus 3 into dou cube dou x square dou y plus 4 into dou cube by dou y cube equal to 0. So we have taken a third order linear PD with constant coefficients. So as per the notation, this becomes d cube of z. This is minus 3 into d square d dash of z, and this is 4 d dash cube of z. So the auxiliary equation will be simply by replace d with m. So m cube minus 3 into m square into 1 plus 4 into 1 cube. So m cube minus 3m square plus 4 equal to 0. This is a cubic equation, and we know that to solve a cubic equation, first of all, we have to identify one root by trial and error method. That is substitute m equal 1, minus 1, 2, minus 2, 3, minus 3 until we get one value of m that satisfies this equation. For m equal to 1, we will get 1 minus 3 plus 4, 5 minus 3, 2. That is not equal to 0. So m equal to 1 is not satisfying this equation. Whereas for m equal to minus 1, this LHS is minus 1 whole cube minus 3 into minus 1 square plus 4. Minus 1 minus 3 plus 4, that is 0. Means satisfy this equation. So m equal to minus 1 is the root of this equation. That means m plus 1 is a factor of this polynomial. So to get the other factor of the polynomial, what we'll do is we'll divide that m cube minus 3m square plus 4 with m plus 1. By log division, we got that other polynomial as m square minus 4m plus 4. So the given equation is same as m plus 1 and m square minus 4m plus 4 equal to 0. But this m square minus 4m plus 4 is nothing but m minus 2 whole square. So we got three roots. From m minus 2 whole square, we got 2, 2, and from m plus 1, we got minus 1. We are naming the equal roots first as m1, m2, and the other root as m3. Then, as per the procedure, the complement function correspond to equal roots m1, m1. You will get some function of y plus m1x plus x into some other function of y plus m1x. In place of m2, we are writing m1. Plus correspond to third root f3 of y plus m3x. Now substitute m1 equal to m2 equal to m3 equal to minus 1, then we will get this. So the complete solution is z equal to CF. So z equal to f1 of y plus 2x plus x into f2 of y plus 2x plus f3 of y minus x, where f1 and f2 are arbitrary functions. So based on this procedure, practice some more problems. So in the next video, we'll discuss non-homogeneous linear PDEs. Okay, bye, good luck.